Hi, Jonathan.
Hello. Sorry, I have this microphone right here. Can you hear me?
Yes, I can hear you fine. I'm gonna give you sharing. Let's see here. All right. Okay, welcome everybody to our next Athena seminar. Glad you all can join. I'd like to introduce Jonathan Rinaldi. He received his bachelor's degrees in electrical and computer engineering from North Carolina A&T State University last May. He is currently pursuing his master's degree in electrical at North Carolina A&T. Jonathan currently works as research assistant with Athena team member, Dr. John Kelly, researching the robustness of federated learning. His initial focus is federated learning applied in a military setting. So with that, I'll introduce Jonathan.
All right, good afternoon, everybody. Once again, my name is Jonathan Rinaldi, and today I will be presenting the federated learning applications and robustness for the military, medical, and transportation environments. Just to highlight my advisors, of course, Dr. John Kelly, Dr. Daniel Limerick, and Dr. Christopher Doss. They are the three advisors to the three subgroups. And then also to highlight some of the people that are on my team, I also have Derek Cummings, who's an undergraduate student, DeWood Ralph, and Seaburn Williams, who are both graduate students as well. There we go. So to begin, as a quick overview of my presentation, I am going to start by providing a background to federated learning in general. Then I will transition into each of the three research domains that we have, starting with my personal group, which will be the military domain, which will also be the main focus of today's presentation. Then I will transition to the transportation subgroup, and then the final subgroup that I will talk about will be the medical subgroup. Afterwards, I will then explain some of the hardware security threats that we are looking into using. And finally, I will open the floor to some questions. So let's get into it. To start, applications of artificial intelligence to the devices that form the Internet of Things raises interesting questions about the trustworthiness and reliability of those devices. So in order to evaluate those risks, the three teams will be creating test beds that will mimic critical IoT systems, and then we will expose each of those systems to different hardware threats. So one of the figures that you see on the right is just federated learning and Internet of Things where they can be applied. And then the figure on the bottom is machine learning and edge computing and how the two of them meet in the middle to have federated learning. Next, I'm going to talk about the goals that we have. So the goals of the three teams are to create and implement different federated learning test beds using different heterogeneous edge devices and import known data sets with those. After we verify that our test beds are working properly, we will then begin to implement hardware security threats to those devices. Afterwards, we will also create our own data sets to be used with our test beds. And then we plan on connecting our test beds to existing research with federated learning frameworks, possibly connecting with researchers working with the edge data centers, and hopefully also researchers pertaining to training devices with tiny machine learning or tiny ML. To give a brief description of federated learning, federated learning is a subset of machine learning where training occurs on multiple edge devices that use their own local data to train the machine learning models. without also transferring their own local data back to that central server. This differs from conventional or traditional machine learning, where all of the local data sets are uploaded and trained on a centralized server. It also differs from decentralized machine learning, where all of the local data samples that are being transferred are identical. So the data will all be the same. For this slide just gives a more physical, seeable representation of how each of the edge devices will receive its global model from the central server, and how they will use their local data, and it will allow them to update their weights and parameters to then send back to that central server. On this slide, I have some variations of federated learning. To start, we are going to start with the graphic on the bottom. This is a more traditional style of machine learning where you have a centralized data lake server. The data there and all of the training happens in that central server. Next, we're going to move to the top left graphic, which is going to be the federated learning aggregation server. With that, as you can see, all of the edge devices, which are the green boxes, and the aggregation server, which is the yellow box in the center, the central server will send the global model to the edge devices. Those edge devices will then train that model using their own local data. They will then send their updated weights and parameters back to the central server, where the central server will then aggregate it, create a new global model, and then send that new global model back out to the edge devices or edge nodes, repeating the process. And then finally, the graphic to the top right is the peer-to-peer variation of federated learning. This is very important because this is the style or variation of federated learning that my group, the military subgroup, will be using. So as you can see, it no longer has a central server. Instead, what happens is each of the edge devices or edge nodes will send out their initial models to each other. Each of those nodes will then use their own local data once again to train those models, and then send their weights and parameters out to each other. And then after that happens, each of those same edge devices will then aggregate those models and then send them back out to each other, repeating the process. And then some of the advantages for federated learning as opposed to conventional machine learning are that with federated learning, there is less bandwidth consumption. And this is due in part to the fact that there are smaller packets being transferred, because as stated before, only the weights and parameters are being transferred from the edge devices back to the central server. And then federated learning also produces smarter models, as well as a lower latency or less or shorter communication time, once again, because the amount of data being transferred back and forth is very minimal. And then federated learning also ensures the privacy of the data on the edge devices. And that part in particular is a key factor of two of the research groups that I will be talking about today. For this slide, we have the three selected federated learning domains, which are our federated learning use cases. The transportation subgroup is going to be looking into the systems of self-driving cars or autonomous cars, specifically the decision-making and road traffic conditions, as well as an intrusion detection system for their subsystems. The military subgroup,
Yeah, I'm on call.
which is my specific subgroup, is working on federated learning in regards to object detection, with the use of UAVs and UGVs, also known as unmanned aerial and unmanned ground vehicles, respectively. We will then also be possibly expanding our research into a pattern recognition system using federated learning. And our third and final subgroup that I will be talking about today will be focusing on federated learning in the medical field, which is focusing on real-time diagnostics using wearable devices and sensors. So to start, I will be starting with my particular domain, which is the military domain. And I wanted to start by giving you all a quick overview of my group's test bed. As previously stated, our test bed will focus on the use of federated learning with the use of object detection with UAVs in a more battlefield-like scenario. Because of that, this is why we decided to go with the peer-to-peer variation of federated learning as opposed to the traditional style of federated learning where there is a central server. We plan on using 3 to 4 clients of heterogeneous hardware. As you can see, we have Raspberry Pis and Arduinos in the graphic to the left or to the right. We will be using the Flower framework for our federated learning framework. And then we used PyTorch to test and verify our object detection algorithm. We will be using CapelliaSim as our simulated environment or simulation medium. ROS2, ROS standing for robotic operating system, and MicroROS for our UAV interface. Basically, that's how the UAV is gonna, or each of the edge devices will collect the data from the CapelliaSim simulator. And then we'll be using MQTT for our communication. We are also looking into the use of blockchain for communication between our devices as well, so that there can be a larger form of trust with that communication. Currently, we were using a sample data set of household objects, but currently we do not have a set in stone military object data set. So afterwards, if any of you have any suggestions of data sets that we could use for that, please let us know. So for the military domains research problem, we concluded that traditional machine learning would not be practical with the use of UAVs and UGVs, especially in a battlefield setting. This is because of the high communication costs stemming from the amount of data that would have to be transferred back and forth between the UAVs and the central server. That also brings us to our second point, being that if there's a centralized server, you then have a single point of failure with conventional machine learning or even conventional federated learning if there's a central server. And this is because in a battlefield setting, if you were to lose that central server because of an attack, you would basically lose your entire system. And our final standpoint on why traditional machine learning isn't viable in that setting is because the data itself is very sensitive, being that it is military data. You do not want your enemy, so to speak, to know what you're looking at or even know your secrets that could be hidden on your devices. So because of this, these issues that I stated in the previous slide, the use of federated learning, especially from a military or battlefield standpoint, will be very beneficial. The use of federated learning not only solves the communication cost issues, because the only data being transferred from in between the UAVs would only be the updated weights and parameters of the models. The use of federated learning also solves the privacy issue for that same reason. And then our group specifically wanted to use, like I said before, the peer-to-peer variation of federated learning because it will be more resilient than the centralized server variations. And this means that even if in a battlefield setting you lose one of your UAVs or you lose one of your drones or unmanned ground vehicles, you'll still be able to perform the federated learning because you'll still have other UAVs in your communication circle. And then finally, my group deemed that the use of federated learning would be very useful in a object detection or object recognition standpoint, as well as if we decide to expand into pattern recognition. Next, this slide gives more of a general process of how our group created our test bed. This process is also very similar to how the other groups developed their test beds as well, with a couple of minor changes. Obviously not in regards to UAVs or UGVs, but with their specific domains. So after we came up with our research problem, we started creating our virtual environment. And for that, we needed a virtual environment or simulation medium, which we chose as Capelliasim. Next, we used a known data set in order to validate our algorithm and validate our test bed, which was the standard household objects not test bed, but data set. We then began importing our edge devices, which in this case are the Raspberry Pis and Arduinos, into our simulation environment and connected them. Our group then used those devices inside of the environment to perform object detection, or we'll be using those devices inside to perform that. And then our final steps for our test beds will be to attack those devices using different hardware attacks, including fault injection and voltage glitching, where our goal is to see how the devices will react after we initiate those attacks. We want to make sure that the data will still be secure and that our systems can still perform the way that they should if those attacks happen. And then if they do not, our future plans will be to create countermeasures against those attacks. So with the test bed setup, the hardware that we are using, or that our research team will be using, consists of 2 to 3 Raspberry Pi 4s and an Arduino Zero. We chose this hardware because, as stated before, we want to keep our testbed environment heterogeneous in terms of hardware. And then the software that we will be using for our testbed will be Capelliasim for our simulation environment or simulation medium, ROS2 and MicroROS for the communication between our hardware and Capelliasim. We used PyTorch basically to make sure that our machine learning algorithm functions properly. We will be using Flower for our federated learning framework. And then the algorithm that we chose to use was the YOLO algorithm, which stands for you only look once and not you only live once. I know we all remember the old acronym. So this slide gives a little bit more of a physical representation of how our testbed is put together. On our host device, we have just a standard laptop computer that is running Ubuntu 22.04 as its operating system. It will have the Capelliasim environment installed on it, and it also has the ROS2 libraries installed on it to communicate with our edge devices. And then our edge devices include Raspberry Pi 4s that are also running that version of the Ubuntu operating system, as well as ROS2. And then our Arduino Zero will be running on MicroROS. So a quick overview of the Capelliasim simulation medium. It's a robotic simulator that we are using because it allows for the control of individual plugins, very much so like ROS2, and other remote API clients. And it can also be used for fast algorithm development for robotic systems in factories, as well as general robotic systems. The reason that we chose Capella Sim is because with it, we are able to create our own environment that we can fully control and modify whenever we see the need to do so. Not just that, we also at A&T have other researchers that are using Capella Sim, Capella Sim as a simulation environment for multiple different scenarios, those of which also include drones and robotics. So we wanted to be able to collaborate with these researchers and possibly use some of the testing environments that they have created with our test bed. And then we also wanted to collaborate in order to possibly help improve the other researchers' test beds and research with the use of federated learning. So we're spreading the love federated learning wise. For the federated learning framework, we are using Flower. The Flower software was designed to help people easily create a federated learning environment. We decided to use this because it does have detailed documentation in case we were to run into any issues with the implementations of it with any of our test beds. It also is not library dependent and allows for the use for its use with multiple different clients at the same time. We will be using it in tandem with our hardware to implement our federated learning with the YOLO algorithm. Then the final piece of our test bed that I will be talking about is the algorithm that we chose to use. So we chose the YOLO algorithm, once again standing for you only look once, as our machine learning algorithm. The algorithm itself is used for real-time object detection systems. It performs this by taking a picture or video and breaking it down into smaller, or breaking it down into blocks or a grid. It then uses deep neural networks to predict what the objects within those blocks will be, and then it will tell you what its predictions are. And one of the main reasons that we decided to use this algorithm over other object detection algorithms is because this algorithm is already in use by both the military and the Department of Defense for object detection. So that fit very well with our subgroups standpoint, being the military. It also can be easily used and run on a Raspberry Pi. And because of that, there are multiple tutorials on how to fully implement and install and run this algorithm on a Raspberry Pi with simple things such as just the Raspberry Pi and a camera. Oh, and the graphic on the right is more of a physical representation, as I said before, of how the algorithm works by taking the picture, breaking it down, finding all the S blocks and boxes and grids, and then predicting what each of the objects inside of the picture are. So to recap, the military subgroup will be using Capella Sim as a virtual environment to simulate how UAVs will perform the peer-to-peer variation of federated learning, to also perform collaborative object detection. Oh, sorry. These devices will also be using ROS2 and micro ROS to communicate to the environment and gather the sensor data. The figure to the right is a representation of how the peer-to-peer federated learning, in this case, it was referred to as the one-hop strategy. And it's basically how each of the UAVs will send as well as receive the weights and parameters from each of their local models from the other UAVs within their communication range or their communication circle, as you can see in the figure to the right. Each of the UAVs will then aggregate those models to then send back out updated models to the UAVs inside of their communication circle. And then once again, to reiterate, we decided to choose this route of federated learning because it negates the need for a centralized server, which makes it more resilient in terms of there no longer being a single point of failure with that system. And because of that, it is very optimal for use on the battlefield. Next, we are going to get into the transportation domain and their federated learning testbed. So with their testbed, their research will be looking into the realm of autonomous vehicles and anomaly detection. With the figure on the left, it shows the IoT networks that an autonomous vehicle interacts with whenever it's driving. Those include the infrastructure, communication to other vehicles, and so on. And then the figure to the right is a representation of how an intrusion detection system can help to protect an IoT system from attackers, but it will also allow trusted and verified communication to other IoT devices. So with the transportation subgroup, they will be focusing on using federated learning to perform real-time road mapping. They will also be implementing and testing an anomaly detection system within the autonomous vehicles network. The transportation subgroup will also be using heterogeneous hardware for their test bed. The main differences being that they will be using a Jetson Xavier in tandem with the Athena Edge Data Center as their servers, and they will be using Raspberry Pis and Arduinos, as well as possibly FPGAs as their clients. And then they also will be using the Flower framework for their federated learning framework with 2 known data sets for testing. And then finally, I'm going to be explaining the medical domain, which is the third subgroup within A&T's research for federated learning. With this subgroup, their focus is pertaining to real-time detection of critical medical events. Very much so like my group, part of the reasoning that they decided to use federated learning, or that federated learning will be more beneficial for the medical field than conventional machine learning, is because of how sensitive the data is and the basically legal requirement for medical data to remain anonymous and secretive and for it to be private. Their testbed will have a similar setup to that of the transportation subgroup, where there is still a centralized server. So far, the transportation and medical subgroups, both of those groups will be using the aggregation server or centralized server variation of federated learning. And one of the main differences between how their testbed is set up versus how the transportation group, how their testbed is set up physically, is that the medical group will be using more Arduinos than Raspberry Pis, as well as they will be using an FPGA to act as a sort of middleman between the Arduino and their Jetson Xavier, which will be their server. Once again, they will also be using Flower as their federated learning framework. They also have used TensorFlow to validate their algorithm. They will be using the All of Us medical data set to train their models for their test bed. But besides that, they will also be gathering their data from the use of wearable devices and sensors. And then finally, to wrap up the presentation, I will be going into the next steps of all of our test beds from here on out. So mainly it is to deal with security or hardware security. So once all of our test beds have been fully set up and validated, each of the groups will be performing hardware attacks against all of the hardware per their test bed. The attacks that we will be focusing on include fault injection, voltage glitching, and clock glitching. And then the figure to the right is a picture of the chip whisperer, which is a piece of hardware that is used to implement voltage glitching attacks on other hardware. And then this slide illustrates how we intend to perform the fault injection in our test beds, in our respective test beds. We also, as you can see the figure on the right, wanted to see if taking over some of the edge nodes in each of our test beds will result in a corruption to the centralized server for those test beds. And then when performing these attacks, the expected results that we have for each of our test beds would be process crashing, masked flips, or even a drop in the accuracy of the algorithms. Once again, we also want to check and make sure that the data will still remain secure. And in an event that after we perform these attacks, these things happen, we do plan on then creating countermeasures to each of those attacks to help prevent that from occurring. Once again, my name is Jonathan Rinaldi. Thank you all for listening to my presentation, and I wanted to open the floor for some questions if we had the time.
Thank you, Jonathan. Any questions? You can write it in the chat or just unmute yourself. Okay, that was great presentation. Thank you.
Thank you.
And I'll be sending the recording out sometime next week. And everyone keep your eyes open. Our next Athena seminar is on May 9th. Dr. Jack Dongara. Thank you, everyone.
Thank you all once again.